This video shows a few automation projects that started with ideas about improvements. Using some design skills, experience, electronics, motion controls, and fabrication capabilities, cost-effective solutions can be created. The goals being to improve productivity, accuracy, and quality. I hope what's shown here is interesting and inspires others to create their own solutions. Sometimes it's just best to buy off the shelf. If that's too expensive or unavailable, then rolling your own makes sense. Here's an automatic stop that sets accurate cuts on boards from 0 to 120 inches. Distances are entered via a keyboard. A pneumatic brake holds the position. This airlock made from two 12-inch blast gates and a section of PVC pipe prevents large volumes of air from a dust collection system being sucked out of the shop. This avoids heat loss in winter and air conditioning in summer. Energy savings are significant. Blast gates are actuated by pneumatic cylinders. Limit switches confirm open and closed positions. A Raspberry Pi 3 single-board computer is used for the control and timing. A wire-wrapped interface PCB provides 4 digital inputs and 4 digital outputs. 4-way pneumatic valves control the air cylinders. The unit is shown here cycling in test mode. Gate timing was adjusted when installed in the dust collection system. The Delta positioner shown presented some interesting mapping problems handled in software. The video shows the software mapping an XY circular pattern into the Delta positioner. All of it run on a Raspberry Pi 4 single-board computer and Gerbil CNC controller. Second-order equations are required so motion isn't linear. As such, straight lines can't be specified as two endpoints but need to be connected short line segments. Same for other patterns. The effector plate, which holds the pen, can be above or below the pivots. This changes the mapping. Note that this is a complex system to get working properly. Use it only if a 3-axis system is justified for some reason. That said, it's interesting to see this work. This jig assembles slats into a cross and staples the two pieces together. Staple ends are bent over to secure the pieces. It can produce about 10 crosses per minute. Slats are fed in from 2 hoppers with a kicker plate at the bottom of the stack. This produced about 150,000 pieces. Software was written and run from an old Dell laptop. The RS-45 Comlink communicated with a 16-channel relay board. That board controlled the pneumatic valves and read limit and safety switches. This allowed the software to know where the process was. A drill with a flexible rubber flap wheel was used to eject stapled pieces. A small conveyor made from nylon rollers allowed the finished pieces to be kicked out. Durability problems surfaced as the jig was used. Since nothing like this was created, it was a learning experience. The concept was valid, however, in that it was possible to automate building the crosses. Better limit switches should have been used, stronger parts, and more durable fasteners. Budgetary constraints prevented more durable parts from being used in the initial design. Splinters from the stapled exits would clog the machine, an easy problem to solve if it was foreseen. It's an example of how automation can be used to make parts. Don't neglect the unforeseen problems and allow time for solutions. Make sure jigs like this are properly maintained and used within their limits. Crosses were used in the mining industry to hold blasting wires. This automatic dump table is used in conjunction with a rip saw to allow ripped pieces to be returned to the in-feed end of the saw. It saves time, avoids extra steps, and allows a single operator to work through a stack of wood faster. Wood is kicked out of the saw with wire brush wheels. This allows it to be fully on the dump table. A switch signals the table that wood is ready to be dumped onto a conveyor belt. The table tilts and the wood falls onto the conveyor where it is returned to the in-feed side of the saw. The table returns to a horizontal position to receive the next ripped piece. The table is controlled by pneumatic cylinders and a 4-way valve. Working out the mechanism to control the dump table was done graphically. Cylinders were sized to provide the required lifting forces. Automation can be complex, simple, or makeshift for one-off situations. The wire cutter used wood, diagonal cutters, air cylinder, stepper motor, and an old DOS PC running indexer LPT. It accurately cut tens of thousands of wires to specified lengths. The automatic wire stripper used dies from a Radio Shack hand stripper to allow quick removal of insulation. This took about 40 hours to make, but saved that time and productivity gains. The jig that located drilling points on 4-inch PVC pipe was made using 2 impact printer heads, stepper motors, small lathe chucks, linear guides, and an Acme lead screw, all of it controlled by an old DOS PC. These projects are some 30 years old now, but examples of what's possible with some ingenuity, even back then with less capable components. I hope you've enjoyed this video and the automation projects it shows. Some projects required partnering with other creators to get ideas and designs at their best. The design tools available now have improved considerably over the years. Same can be said for automation components where prices have dropped and quality has improved. Edison remarked, "Genius is 2% inspiration and 98% perspiration." Thanks for watching.